a device using a 4-active ARM Wheatstone bridge, and one would ask why 4-active ARM? That would simply be for convenience and accuracy when you're designing your strain gauge, you're testing. So for instance, let's say if I were to draw a beam over here, and we're trying to see only the tension force on the beam. If I were to attach one strain gauge over here, and with the rest, let's say it goes out, and then I connect my Wheatstone circuit over here, this strain gauge would be the 2 points, and I have resistance. What's going to happen, let's say I applied a bending force to the beam. If I would apply a bending force, then this strain gauge would have a strain, because it would have something like this. If I could, yeah, this is how the strain gauge would look. And you can notice that there is some strain happening on that side, although this is kind of the opposite. This is being compressed and that being strained. But regardless, there's some strain difference, which means there would be some resistance change, which means there would be a voltage reading. So the reason we're going to use all of them as a strain gauge is because the next one we can put as, let's say, parallel to it. Which means then if there was a bending, then there would be some change here, and there'll be another one, let's say, perpendicular to the surface. And in that case, if we arrange it in a proper fashion, what we can have is canceling out all other forces, all other moments except this tension force in this direction. We can call it x direction. So then the question is asking, so we have all these 4 resistance as strain gauges. We're trying to design an amplifier circuit to output entirely in the linear region. And we know that from the data sheet that the arm deviates by plus or minus 0.3%. The resistance, again, will also be found from the data sheet. And I'll just point out that throughout the video, I'm not going to be using hard-coded values, as in, let's say, the voltage would be 5 volts and the op-amp would, let's say, get out 20 volts. I'll just keep it as V op-amp, V of the Wheatstone. And with that, it could be a little more generic, the equations we derive. Okay, so what we're going to have to do is make an assumption over here. And it comes with this. This positive terminal is going to be connected to here. And this negative terminal will be connected to the negative terminal of op-amp. You know the gain of the op-amp is going to be an R4 over R3. Subtract these two. But what we're going to have to do is understand that what kind of resistance would be seen if I would connect this input over here. Why we're trying to do that is to find the maximum power transfer. Because if that wasn't the case, then you can answer it anyway. But what I'm trying to do is the maximum power transfer. In other words, take the most energy from here into this op-amp so that the op-amp can use the least amount of energy to output it. If I were just to care about the most accurate data, then you'd probably use the highest impedance. But again, then that means the op-amp would have to take almost all the power, more than would be needed if you try to use the maximum power transfer. So if I were to create that circuit over here, what's going to happen is we're going to have to reference this as ground. As let me just see the next. Yes, so we have this is ground, which would allow us to, let me pull out the pointer, which would allow us to connect these two together. If these two are connected together, then what's going to happen is that these two resistances are not going to be required because the electricity can go through at least current path. So in other words, then to find out this load resistance over here, using the maximum power transfer theorem, we would have to find the source resistance. To find the source resistance, we short out the circuit, and we notice that these two are in parallel, which means the resistance of the source is just going to be the resistance of one strain gauge divided by 2. But then that's equal to this is our load, which is then equal to R3. Because we said that the load would simply be R3 because of the virtual ground occurring at the op-amp terminal. So once we find R3, then it should be a lot more easier to solve the question. So we have over here the linear region of an op-amp. Red is op-amp, and blue is the exaggerated version of the Wheatstone bridge. It's really going to be, let's say, 0.1 of a volt or something like that. We have the voltage, let's say call this V of the op amp max. It could be 20, it could be whatever you want. How do I find out what gain is required? Well, the gain required is going to be the ratio of this portion to the ratio of this portion, which means the V of the max op amp over the voltage maximum of the source. But again, what's the voltage maximum of the source? Well, then my source can only change. Let me pull out the pointer one more time. My source can only change by plus or minus 3%. And because it's a Wheatstone bridge and it's balanced, that correlates directly to the input voltage. So, in that case, I can mathematically write that as the V, the max of the source, is going to be equal to the V, which is of the Wheatstone bridge, which is times 0.003. And with that, you can plug in here. And then we know through op amp, the gain of it is simply R4 over R3. And you can use that from the original op amp using superposition to see what the positive and negative terminal would have been. But it will turn out it's R4 over R3. You can plug in the values for the resistance, it should be easier. But because we have a general equation now, we can tweak it to whichever, let's say, data sheet. If the resistance of the strain gauge changes, we can simply use it in. This question is really an advanced question, has many concepts to it, and it took me particularly a lot of time to try to find out that answer. But this should be the solution to the problem.